Assalamu alaikum students. Our next topic is Rolle's theorem. According to this theorem, it states that let f be the continuous on a closed interval ab and f be the differentiable on an open interval ab. And the third condition is f of a is equals to the f of b, and where the b is greater than a. Then there exists at least one number such that c belongs to the open interval and f dash of c, or we say that f derivative of f at c is equals to the 0. So in this, according to this theorem, we have a function y is equals to f of x. Let y is equals to f of x. We have a function, okay, and the function have the three conditions. The three condition is that the first condition is the function is continuous, and the second condition, the function is differentiable on an open interval, and the third condition is that the ending points, or we say that the starting points of on the interval, the function's value is equal. Okay, and then we have to prove that if the function have these three conditions, then there exists at least one number in the interval that we say that is a c. Then the derivative of the function at c is 0. Okay, if we have to draw first of all the graph of the function. Let's see, according to these conditions, we have a graph of the function is like that. Okay, and where the curve is y is equals to f of x, and we say that the ending points, at the ending points, let's suppose there is a and there is b, then f of a, we say that the points are a and f of a. Okay, and the point is b and f of b, and we have to show that there is a point c. Let's suppose this point c is this there, and the derivative of the point is c is equals to 0 at c is 0. And according to this condition, if we revise the definition of the critical point is the same as here. And now we have to prove this theorem according to this graph and the conditions. So for this the Rolle's theorem, according to this equation, we have two cases. The first case is that y is equals to f of x and is equals to k, and where k is constant. So we have the function is constant. Then we have the conditions is, if we find f of a, then it is k, and also we have find f of b, it is also k. Okay, and now if we find the derivative of a constant function, that we know that the derivative of a constant function is 0, and according to, if we have any c number in the interval a b, then the derivative of the function at c is equals to 0, and we prove the condition when the function is a constant. Okay, and the second case is that the function is not constant. According to this, y is equals to f of x, and f of x is not equals to k. That means f of x is not a constant function. So according to this, let's suppose an positive, non-positive, or we say that a non-negative real number. Let's suppose it is h, and if we, according to this interval ab, we have if we draw the real line, then we say that there is a and there is b, and this c is sum is for example sum is here, then we say that, and the h is very small, and h is very small. Then if we added some thing in C, then we give up here, goes to there, and we for example, let's suppose C, we added some C, then we go here and we subtract some from C, very small value h, then we have goes to the lower values. Okay, and if we see according to the graph, then let's suppose if there is a C, then if we goes back according to this graph, then we have the values. Okay, according to the graph, if the C is here, then f of C is here. And if we have a value, let's suppose f of C and f of C plus h. We see here the f of C is greater than the f of C plus h. Let's suppose here the value of the function is decreasing here. Then we see we write here f of C is greater than equals to f of C plus h. That means f of C is greater than f of C plus h here, because the value is decreasing. And another way we say that if we have C minus h, then f of C and f of C minus h, then also the function's value is, if the f of C is here, then there is the function's value is also decreasing or lower values. Then we also say that the f of C is greater than equals to f of C minus h. If we solve these inequalities, then we have 0 greater than equals to f of C plus h minus f of C. And here 0 greater than equals to f of C minus h and minus c. If we have to find out according to the definition of different derivative, then we have, if we divide both these inequalities with h, here is also h and here is also h, then we get 0 is greater than equals to f of C plus h minus f of C and over h, and here 0 greater than equals to f of C minus h and minus c f of C over h. And we say in the starting that we consider the h is very small. Let's suppose the C is approaches to 0. It is very small increment or the change and very small number, real number. Then if we say that the limit h approaches to 0, and according to this, if we use this limit in the inequalities, then we write here 0 greater than equals to limit h approaches to 0 and f of C plus h minus c f of C over h. And we also write here 0 greater than equals to f limit h approaches to 0 f of C minus h and minus f of C over h. And according to the definition of derivative, we have something here. Students, let's see. We have f of C plus h. Like if we write here that f of x plus h and minus f of x over h and limit h approaches to 0, then we have the derivative at x. Then we also write here 0 is greater than equals to the derivative of f at c. And but here with the inequalities, we have not the increment, we have like minus h. If we say, and we have also according to this the same condition is here, so then we can be write here as limit h approaches to 0 and if we write here f of c plus into minus h, then there is no problem, and minus f of c over h. And we have need here minus, then we divide or multiply the minus on both sides. Then according to the condition of the inequality, the value is here 0 is less than equals to, and limit h approaches to 0, and f of c plus into minus h minus f of c and over minus h. Then we also write here that 0 is less than equals to f dash of c, or the derivative of f at c. And now we have the something, there is 1 and 2. According to the inequalities of 1 and 2, we have something that we 0 greater than equals to f dash of c, and 0 is less than equals to the f dash of c. Then we say that by 1 and 2 inequalities that f dash of c must be equals to 0, because we have some condition. If we have x greater than equals to y and x less than y or equals to y, then we can be say that x is equals to y. So according to this condition, we also say here if 0 greater than equals to f dash of c, then and also 0 less than equals to f dash of c, then we can be say that f dash of c is equals to 0. So we have the condition, and we have solved the question that if we have these three conditions, and that then there must be exist at least one number in the interval at which the derivative of the function is 0. And we have two cases. First of all, we have the function is equals to the constant, and the other when the function is not equals to the constant, and we can be use the properties, and we solve that the condition that the derivative of the function at that point is equals to the 0.